Hello everyone. Uh, Welcome to problem solving session for week 3. So before we start, let us wait for a couple of minutes so that if others want to join, they can join. Meanwhile, if you want to ask any doubts that you have, feel free to unmute yourself, or you can type your doubts in the chat box, whichever way you feel comfortable.
Good afternoon. Am I audible?
Good afternoon. Yes, you are audible.
I have a doubt in question number 7 of week one's assignment. I asked it last week too, but since the due date was still there, so you
Yeah,
said,
yeah, yes. Right. The due date is over now, right?
yeah.
Okay, one sec. Let me pull out that question. Hmm. Okay. Yes, I have got it. It is regarding a particle that is moving along a straight line in two dimensions, right? XY plane. Correct?
Yeah.
Okay. So, what do we have? So, what is your doubt? Do you want me to solve it, or how should we proceed?
Uh, you can solve it. I did try it, but I wasn't getting any good conclusions from it. I I drew a vector, r vector, and assumed some random coordinates xy.
Mm-hmm.
Then I used the condition of it being a straight line.
Mm-hmm.
I wrote the condition as y is equal to mx, where m is the slope.
Yes.
And
Okay.
then I used that condition and wrote r vector is equal to xi cap plus yj cap
Mm-hmm.
and substituted the value of y as
Okay.
mx.
Yes.
So using that, I also derived this equations for velocity, acceleration, and torque too. But I didn't get any meaningful solution from it. I
Okay.
wasn't able to conclude anything related to the options.
Got it. Hmm. And answer key is also out, right?
Yes.
So, like, does your answers match with the answer key given or not?
No. Some options match. It's
Okay.
a multi-select question.
Yes, yes.
Three match. Three match with the answer key. One of them doesn't.
Okay. So, okay, okay. Okay, so yeah, we can, of course, we can solve this one. So let's start with this one. Okay, so we have a particle moving along a straight line in two dimensions, and then they are asking which of the following cases are possible. So let me write down the options. First option is particle is moving with constant acceleration uh, in both x and y directions, right? So constant acceleration in x and y directions. This is option A. Particle has force acting only in x direction. Force acting only in x direction. The particle is experiencing zero force. One sec. Okay. So net force is equals to 0. Option D is particle has non-uniform acceleration in both x and y directions. So non-uniform acceleration in both x and y. And finally, torque acting on the particle is non-zero. So torque not equal to 0. This is it, right? And the correct options that are given are, I think, this one, and this one. Is that correct?
Yes.
Okay. So, okay, okay, let's do it. So first of all, let's draw an xy plane. Let's say this is my xy plane. Xy plane. And now it is said that our particle is moving along a straight line in this xy plane. So you have taken the straight line to be something like this, correct? And the equation is y is equals to mx. Okay, so it is passing through the origin. Okay, so when it is moving along this line, so let's say our particle is here. So when it is moving along this line, so its velocity is either in this direction or opposite, right? Let's consider it is moving forward. So the direction of velocity is not changing with time, right? Okay.
Yes.
Its magnitude can change, but its direction cannot change. That is the constraint. Okay, right. So constant acceleration in x and y. So then, because let's say let us write it like this. So we have okay, okay. So we have r is equals to x I cap plus y j cap, right? And the velocity v will be vx I cap plus vy j cap. Okay, and this mm, so the velocity vector. So if I write v as this, like this magnitude times the vector, then we know that v cap is constant, right? It's not changing with it. So then they're asking, like, is this situation possible? So of course, if you can have constant acceleration in x and y, this is of course possible, right? For example, zero acceleration is also a constant acceleration. So that is one special case. I can choose my acceleration to be zero, and I can even choose my acceleration such that the particle continues to be on this line. Okay. So what that means is either my a is zero or my a cap is parallel to my v cap, so that the direction of this acceleration is along the direction of my velocity, right? So the particle will only speed up, it will not change the its trajectory, right? So option 1, constant acceleration in x and y, yeah, that is correct, that is possible. Okay, so any doubts for option A? You want to ask anything?
No.
Okay, so force acting only in x direction. Okay, so if my force is acting only in x direction, then what will happen? So there is no, so my a cap, then basically my a cap is only along x direction. So a cap is only along x direction, right? So x cap. So if my trajectory were to be parallel like this, then this would have been possible. But for a general any straight line, this statement is not true. Correct? Because we have established this thing. There's my that my acceleration and my velocity, they have to be parallel to each other. Right? So for any general line, y is equals to mx, this condition is not always true. Okay, this is only true when my velocity is parallel to x-axis. So any doubts in this one?
No.
Okay. So right, so this third one is very straightforward. So the only requirement is that my particle moves on this straight line. So is it possible that a particle is moving on a straight line and the net force acting on it is zero? Do you think it is possible? Of course it is possible, right?
Yes.
This is the first law of Newton, right? It can have a constant velocity and net force will be zero. It will continue moving on that straight path, right? So this is of course possible. Now non-uniform acceleration in both x and y. So what do you mean by non-uniform acceleration?
It is changing with respect to something, mostly time.
Mostly time, yes. Right. So okay, so acceleration along x is changing with time and acceleration along y is also changing with time, right? But it can it, like the question is, can it change in such a way that although the independent components are changing with time, but my a cap, right, the direction of my vector, that is always parallel to v? Is that possible? That is the question. Do you think it is possible?
Yes, it is possible.
It is possible, right? If both of them have same dependence on t, right? Let's say one of them is, let's say my a, I can write, let's say 4t I cap plus 2t j cap. So when I take their ratio, the t and t will cancel out. Correct? So if they have same time dependence, linear in t or maybe quadratic in t or whatever, so my a cap will be fixed. A cap is fixed, and that I can set parallel to v, and that is possible. So any doubts for this option?
No.
Okay. So then is your doubt regarding the last option?
Yes.
Okay. So the last option is it possible that I have a non-zero torque? Okay. So I have some finite torque and still I have a linear motion, right? I have this motion in a straight line in the xy plane. Okay. So the torque acting on the particle is non-zero. That is my last option. Okay. So let me quickly erase this thing. Okay. Now torque depends on my, like, on the point that I am willing to choose. Okay. So because torque is r cross f, so it depends on my origin. So if a particle is moving in a straight line and the force is pulling it along that line, the torque will be zero, right? So the so let's say this is my particle, right? And so the r vector will be like this, right? This will be my position vector r. Okay. And this particle is moving on a straight line. And if my force is also acting along that line, so what will happen? My r cross f will be zero, right? So r cross f, my force is also along this line. So my r cross f is zero, right? Because, okay, let me explain again. So my position vector is along this direction, along this line. Also, my acceleration is along this line, right? And because my acceleration is along this same line, so my A is parallel to V and it is also parallel to R cap. So my this cross product has to be zero. Okay.
Yeah.
Okay. So if this is non-zero, that will mean that there is some additional component of f which will be perpendicular to my path, that is going to give me a net non-zero torque, right? And if we have some non-zero force component, then our particle will not follow a straight line anymore. Does that make some sense?
Yes.
Right. So we cannot have a non-zero torque if we are considering a linear motion. Okay. So any doubts? Any other doubts you want to ask? Is this clear?
No, just this one. Yes.
Okay. Huh. Okay. So before I start, so before we start today's session, I have some problems. And before starting, if anybody wants to ask anything regarding week three, or prior to week three, you can unmute yourself and ask. Okay, no problem. So then let us. Okay, so let us start by solving some problems. And so first five problems are very straightforward, like kind of warm up problems. So we'll go through them little quickly. If you think I am going too fast, you can unmute yourself and ask me to slow down. That is not a problem. But mostly the problems for these questions 1 to 5 are based on week 1 and week 2. So like a revision kind of problems, and they are very straightforward. So we will not waste much time and consider it more like a warm up. Okay, so let us begin. So we are given that we have a particle of mass m is equals to 2 units. Okay. And the position vector as a function of time is given to us. So this is the position vector as a function of time. And use this particle for questions 1 to 5. So for the next 5 problems, we'll consider that this particle has mass m is equals to 2 and this is the position vector given to us. So this is a two-dimensional problem, right? The position vector is given in terms of I cap and j cap, and its position is changing with time. So let us do this one. So we are given that our r of t, so the x component is 2t cube minus 3t I cap and t squared plus 4 j cap. Okay, so first question is find the velocity and acceleration of the particle at t is equals to 1. Okay, so we know velocity is dr by dt. So let us take its derivative. So this becomes 6t squared minus 3 I cap plus 2t j cap. And velocity at t is equals to 1 will be, so this will be 6 minus 3 is 3 I cap plus 2 j cap. Okay. Similarly, my acceleration a of t, I can write as dv over dt, and that will become 12t I cap plus 2 j cap. And acceleration at t is equals to 1 will be 12 I cap plus 2 j cap. Okay, so 12 I cap plus 2 j cap. So BC or E. And then this is 3I plus 2j. Okay, I think option A, right? Yes. So the correct answer is option A. Okay, so I mean, it was kind of straightforward. Just take derivatives and put the value of t. So let's move on. Okay, find the kinetic energy of the particle at t is equals to 1 and t is equals to 2 respectively. So the kinetic energy we know is half m v squared, or we can write this as half, regarding at we don't have j cap. No, we have j cap here, but it is constant. Yeah, so this is a of t and this is v of t. Okay, so you can see this at has a j component, but it is a constant component. It does not depend on t. Whatever, let's say t is 10 seconds, it is still 2 j cap. If t is 0 seconds, it is still 2 j cap. So there is no time dependence. It is just a constant acceleration. Okay. And so this is our v. So vt is 6t square minus 3 plus 2t. So let me write here that our v of t was given by 6t squared minus 3 I cap plus 2t j cap. So my v squared I can write as v dot v. So that becomes 6t squared minus 3 whole squared plus 4t t squared. Okay, this is my v squared. Therefore, my kinetic energy becomes half m 6 t squared minus 3 whole square plus 4 t squared. And now I have to find the kinetic energy at t is equals to 1 and t is equals to 2 respectively. So Ke for t is equals to 1. Okay, and also my m is given to be 2 units, right? If you recall, my m is 2 units. So this half and m, they'll cancel out. Okay, so I can cancel these two out. And at t is equals to 1, this just becomes 6 minus 3 whole squared plus 4. And this is 3 squared plus 4. So 9 plus 4 is 13 units. And kinetic energy at t is equals to 2. So this will become 6 times 4, 24 minus 3 squared plus, and now this 2 squared is again 4 and 16. So this becomes 21 squared, which is 441 plus 16. So 457. Okay. Again, option A. Hmm. Okay, so we knew velocity, and from velocity we could calculate kinetic energy at these 2 points. So moving on. Using the work energy theorem, calculate the work done on the particle between t is equals to 1 and t is equals to 2. So what is the work energy theorem? W is equals to change in kinetic energy. Correct. So let us write. So my work is change in kinetic energy. So it will be kinetic energy at t is equals to 2 minus kinetic energy at t is equals to 1. So this was here 13 and 457. So this will be 457 minus 13, which will give me 444 units. Okay, which is again option A. Okay, so this is called work energy theorem, that all the work done by the force gets converted into kinetic energy of the particle. So the difference of this kinetic energy, delta E, is equal to the work done by the force. Okay, pretty simple. Uh, right, so calculate the torque acting on the particle about the origin at t is equals to 2. Now torque, we know, is given by R cross F, right? So my torque tau is R cross F. So first of all, let me find out F. So my F is, sorry, my F is mass times acceleration. And this will be, so I had written acceleration here already, this 12t plus 2. Okay, 12t, so m into 12t I cap this must be hmm. Okay. 12 Ti cap plus 2 J cap. Okay. Now my M is 2 units. M is equals to 2 units. So my force then becomes 24 Ti cap plus 4 J cap. Okay. And also let me write down my R here. So my R was given to me. Right. So this is my R. 2t cube minus 3t and t squared plus 4. Okay, so I have my R and I have my force here. Okay, and so both my okay, so I have to calculate the torque about the origin at t is equals to 2. So at t is equals to 2, my R is that is given by this will be 8, 16 minus 6, 10. So this will be 10 I cap. 2 square is 4 plus 4. This is 8 J cap. Okay. And my force at t is equals to 2 will be 24 times 2 is 48. So 48 I cap plus 4 J cap. Okay. And so both my R and F are along the xy plane. So my torque will only have a k component. So let me write tz component. That will be Rx Fy minus Ry Fx, which means this will be 10 times 4 minus 8 times 48. So this will be 40 minus 8 4 uh, 384. So I subtract, this gives me minus 344. So my torque is minus 344 k cap units. Okay, which is option A. Okay. And finally, based on answer to question 4, is the force acting on this particle central with the origin as center? So can anyone of you answer this question? We just calculated our torque, and can we say anything about the force acting on this particle? Like is it a central force? So we have option A, that yes, it is a central force because angular momentum is constant. Option B is no, the torque about the origin found in question 4 is non-zero, so F is not directed purely along R. For option C, we have yes, because kinetic energy increases with time. Option D, no, because the particle speed is not constant. And option E cannot be determined from the given information. No, torque is non-zero, L won't be constant, thus not a central force. Which means, which option? Uh, Option B, right? Option B. Okay, great. So, because we found a non-zero torque, that means our angular momentum is not conserved. But we know that for a central force, angular momentum is always conserved, right? Okay, so option B is correct choice. Okay, any doubt in these first 5 questions? I mean, I rushed through them a bit, but they were fairly easy. So, anybody has any doubts? No? Okay. Then let us move on to some central force problems. Hmm. So, we are given a particle which moves in a circular orbit. Okay. So, the orbit is circular, and we are given that the attractive central force F of r is minus k to the Rn. So if the orbital time period t is found to vary with orbital radius as r squared, t proportional r squared, find the value of n. Okay. So now let's let's do some central force problems. Uh, okay. So okay, let me first give you a brief kind of equations, right? Let's write down the equations for a central force. So we know that for any general central force, right? For a general central force, F of r. Okay. So it acts only along the radial direction. There is no theta component of this force, right? So from Newton's second law, we get two equations. So we get a radial equation, which is m r double dot minus r theta dot squared. This is equals to f of r. Okay, so this is Newton's second law written for the radial component, and for the angular component or the transverse component, this equation becomes m r theta double dot plus 2 r dot theta dot is 0, because there is no transverse force acting, right? There is only a radial force. There is no theta component of the central force. So this we set to 0. And from this second equation itself, okay, from this second equation itself, we are able to write this thing, that the time derivative of m r square theta dot is 0, and this is nothing but angular momentum, right? This is L. So my angular momentum L, which is mr square theta dot, that is conserved. This is all about the central force problem. And using this thing that my L is conserved, I can write my theta dot to be L upon m r squared. And then I can substitute this back to my first equation, my radial equation. And what that allows me to do is just write a r dependent equation. So we can completely get rid of theta. And so my equation becomes m, so this will remain m r double dot minus r and this theta dot squared. So let me write mr, and for theta dot squared I'll have L squared over m squared r to the power 4 is equals to f of r, and then I can write this as, sorry, I can write this as m r double dot is equals to f of r plus L squared over m r cube. Okay, so this is just a one variable problem now. We only have one variable, which is r. One sec. Hmm. Okay, sorry, I lost my connection. Sorry, I lost my connection. Am I audible now?
Yes, you are.
Okay. Okay, so what I was saying is using my conservation of angular momentum, I have now reduced it to just a one variable problem, right? And in last class, what we did, we just we could write, let's say if I can write my f of r as a derivative of a potential v of r, and I can write my L squared over mr cube as minus derivative of L squared over 2mr squared. So basically what this will allow me to do is I can then write my mr double dot as minus d over dr of this thing v plus L squared over 2mr squared. And this entire thing is what we defined to be effective potential, right? This is my effective potential, and this is what we discussed in one of our last sessions as well. Okay, so this is like a basic background for our central force problems. Now, keeping all these things in mind, okay, now we'll do this problem. So we are, now let's read the problem again. We are given a particle that moves in a circular orbit, and the central force varies as minus k to the power Rn. And if the orbital time period tau is found to vary with orbital radius as t proportional r squared, find the value of n. Okay, so here we are. Now, when we are given a circular orbit, so for circular orbit, what will happen? My r is a constant, right? Let's say it is some capital R and it is a constant. Okay. So if I put my r as constant here in this equation, so my left hand side becomes 0. Okay. So basically what I get is I get d of v effective by dr. For r is equals to r, I get 0. Okay, this is what I get. And if I go back to my earlier equations here, so let us focus on the radial component. Okay, so for my radial component, my first term goes to 0, so r dot will be just 0, and what I will have is the centripetal force, right, minus mr theta dot squared. Okay, so what I will have is I will have minus mr theta dot squared, which is my centripetal force, that is equals to f of r, and this I can write this r also as my radius, and this f of r is given to be minus k to the power rn, so it will become minus k to the power r of n. Okay, so this implies that my theta dot squared, which is my omega, right, omega squared, this is proportional. Okay, so let me write theta dot squared, so this is k to the power rn over mr, so I can write it as k over m r to the power n minus 1. So my theta dot squared is proportional to r to the power n minus 1, which implies that my theta dot is proportional to r to the power n minus 1 by 2. Okay, and also my time period t is nothing but 2 pi by omega, and omega is theta dot, so 2 pi by theta dot. So this implies that my t is proportional to, so this is n minus 1 by 2, so minus of n minus 1 by 2, right? So r to the power minus n minus 1 by 2, which implies that t is proportional to 1 minus n over 2. Okay, and in the question we are told that t is proportional to, sorry, this will be r. In the question we are told that t is proportional to r squared, right? So combining these two, this one and this one, I can write my 1 minus n over 2 is equals to 2. So this implies 1 minus n is equals to 4, which implies n is equals to minus 3. Okay, so n is minus 3, which is option C. Okay, any doubts in this question?
No, sir.
Okay, good. So let us move on. Okay, so this time we are given a particle and we are given both the uh, r component and theta component. So we have to find the transverse component of acceleration at t is equals to 1 and state whether this motion is consistent with the central force about the origin. Okay, so first of all, in polar coordinates, we know that our acceleration has two components, right? So our acceleration A, so it has a radial component which goes like this. Sorry, r theta dot squared r cap, and r theta double dot plus 2 r dot theta dot and theta gap. Okay, so now we are given two things. So first of all, my r of t is 2 plus t squared and my theta of t is log 1 plus t. Okay, so let us find out all these components. So first of all, my r dot of t will be just 2t and my r double dot is just a constant 2. Similarly, my theta dot of t, derivative of ln 1 plus t, is 1 over 1 plus t, right? And my theta double dot of t is minus 1 over 1 plus t squared. Okay. So at t is equals to 1, that is what the question asks, right? The question asks at t is equals to 1. At t is equals to 1. So my r will be, so this is 2 plus 1, 3. R dot is 2. Okay. Theta dot is 1 by 2. And theta double dot is uh, minus 1 by 4. Okay. So the question asks that what is the transverse component. Okay. So by transverse component, we are asked about this component, the theta component. So it is simply r theta double dot plus 2r dot theta dot. So the transverse component a theta at t is equals to 1 is simply r theta double dot. R is 3. Theta double dot is minus 1 by 4. Right? And then plus 2 times r dot is 2 and theta dot is 1 by 2. Okay. Right. So this becomes, so these two cancel out and this becomes minus 3 over 4. So minus 0.75 plus 2, which is equals to 1.25, right? So my a theta is equals to 1.25 units. Okay, so it is either option A or option C, right? But we also need to state whether this motion is consistent with the central force about the origin. So which one will it be? Do you think it will be option A or option C? Option A, not consistent with the central force. And what is the reason that it is not consistent with the central force? That a theta is not equals to 0, right? Just in the previous case, we saw that this transverse component has to be equals to 0, right? This transverse component has to be equals to 0. But here we are getting a non-zero transverse component, which is why this is not consistent with the central force. So option A. Okay. So okay, so for the week 3, I hope now this time we were taught about this Binet equation, right? Yes or no? Mm, we skipped this problem from last session, if you remember.
It was the problem of Hessian matrix, I think, that we skipped in the last class.
Yeah, yeah. We skipped bunch of problems. This was also there. This was one of the problems. Okay, so anyway, we are taught about this Binet equation, right, in this class? Uh, yes, no?
I cannot say, I haven't watched the week 3 lectures yet.
Okay, I think it is covered, but okay, anyway, okay. Let me give you a brief overview of what this equation tells us, right? Why do we need this equation? Okay. So, hmm, so we wrote one equation for a central force, right? The equation was that this radial component of Newton's law, mr double dot minus r theta dot squared, this has to be equals to my radial force f of r, right? This is the equation. So this is a differential equation in time, right? We are differentiating with respect to time. But if we want to find out the shape of the orbit, okay, if my orbit is circular, parabolic, like what is the shape of this equation, then we don't need the time dependence. And what we actually need is how my r is changing with theta. Okay, so from r of t, I want to go to r of theta. Okay, so basically then what I need to do is I need to change the independent variable from time to my angle, right? From t to theta. And what is the one equation which will allow us to do that? It is the equation of angular momentum, right? So we know that our angular momentum m r squared theta dot. We have this equation. Okay. So now, okay, so it is given here for u theta is equals to 1 over r theta. Let me substitute this thing. So if I substitute my u of theta as 1 upon r theta, so what I'll get? So I'll get r is equals to 1 over u. So this allows me to write my L as m theta dot over u squared. And this allows me to write my theta dot as L u squared over m. Okay, so what I have done, I'm instead of writing r, I'm writing the reciprocal of r, which is u. And you'll see why we are using u shortly. Okay, so first of all, here we have r dot. So let us convert r dot into a theta derivative. So my r dot, which is dr by dt, I can write it as dr by d theta and d theta by dt, which is simply theta dot. And theta dot I have here. So this is nothing but d over d theta, and r is 1 by u, and here I have theta dot. So d by d theta of 1 over u, this gives me 1 over u squared, right? Minus 1 over u squared du by d theta, correct? And for theta dot, I can substitute this lu squared over m. So these u squares will cancel out each other, okay? And what I will get is, I will get my r dot to be equals to minus L over m du over d theta. Now, if I want to find out my r double dot, that is simply d by dt of this thing, which is minus L over m du by d theta. So this L over m comes outside. So let me write minus L over m, and this becomes d to u by d theta squared. And again, I'll have one more theta dot here. Okay. And then I can substitute for this theta dot. I can again write this as Lu squared over m, and my r double dot becomes minus L squared u squared over m squared and d to u by d theta squared. Okay, so this is my r dot and this is my r double dot. So you can see I have replaced my time derivatives. So left hand side are the time derivatives and right hand side are now theta derivatives, right? So from time I have successfully gone to theta. So if I substitute this back to my this radial equation, so what I will get? So my mr double dot instead of r double dot, I will have m minus L squared u squared over m squared d2u by d theta squared minus, so this second equation, which is r theta dot squared. Okay, so my r theta dot squared, so r is 1 by u and theta dot squared is simply lu squared over m whole square. Okay, and this is equals to f of 1 over u. Okay, so now this thing becomes, I can take out this minus L squared u squared over m outside, and inside I'll have d to u by d theta squared, and here I will have, so this m cancels out, this thing goes here, and I'll just have one u remaining. Okay, and this is equals to f of 1 over u. Right, so finally I can write my differential equation d to u by d theta squared plus u. I can write this as minus m f of 1 over u L squared over u squared. Okay, and this is my Binet equation. Now in this equation, you can see there is no time dependence, right? So it is just u as a function of theta, right? So this is just the orbit shape, right? Because u is nothing but 1 by r. So if we know how my force varies with my 1 by u, which is nothing but r, I can easily find out how my r varies as theta, right? So basically this just gives me the shape of my orbit. Okay, so if u is 1 by r, which was given in the question, if u of theta is 1 of r or theta, and then which of the following is true. So option A, right? So this option, this is known as Binet equation. Okay, so I have derived it for you. I hope it was derived in the class also. I could not attend the class this week, but yes, here you have it. So this is how we derive the Binet equation. Essentially, what we are doing is we are removing this from this t, we are going to theta. So all the time derivatives we are changing to theta derivatives. Okay, so any doubt in this one? Because now we'll what we'll do, we'll apply this equation to find out some orbits. Okay, no doubts. Okay, good. So huh. Then let us solve this problem. So a particle moves along this logarithmic spiral. R is a e to the b theta. And then using this Binet equation, we need to determine the nature of the central force which is responsible. So the equation of R is given to us. R goes as a and then e to the power b theta. This is the equation of R given to us. And then we are asked to use the Binet equation. So first thing that we do, if you remember, we write what will be the corresponding u, right? So my u, which is 1 by r, that will become 1 over a e to the power minus b theta. Now this is my u, and in this equation you see I have to find, I need u and I need a second derivative of u with respect to theta, right? So this is my Binet equation. So let us find out d2u by d theta. So first of all, my du by d theta, that will be minus b over a e to the minus b theta, okay, which is nothing but minus bu. And my second derivative, d2u by d theta squared, will be simply b squared by a e to the minus b theta, which is nothing but b squared u. Okay, so this is it. Now if I substitute it in this equation, what I'm going to get is, so my left hand side becomes b squared u plus u. So b squared plus 1 times u. So this is my left hand side. So b squared plus 1 u. This is my left hand side. And my right hand side is minus mf upon l squared u squared and then f. So minus m and then f of 1 over u over l squared u squared. Okay, so then if I were to write my f of 1 over u, that simply becomes minus L squared 1 plus b squared u cubed over m, right? And now let us substitute back. Let us again go from, let us put this as u as 1 over r. Okay, let us put this thing back here. So my f of r becomes minus L squared 1 plus b squared over m multiplied by 1 over r cube, which means that my f of r is proportional to minus 1 over r cube. Okay, so 1 over r cube. So okay, we have two options here, A and C. Is the force varying inversely with r cube? Yes, the force is varying inversely with r cube, but what do you think? Is it attractive or is it repulsive? Attractive, because we got this minus sign here, right? This minus sign makes it attractive, correct? So option A. Okay, next problem. We have a particle of mass 3 units that moves under a central force such that this r square omega is 6 units, constant by conservation of aerial velocity. Find its angular momentum L. Okay, 18 units. Yes, 18 units. So it's kind of application of Kepler's law, right? This is what we call as Kepler's law. So conservation of aerial velocity means, so my dA over dt, okay, let me write here, my dA over dt, this is my aerial velocity, that is L over 2m, okay, which is half r squared theta dot. Okay, and since my angular momentum is conserved, my mass is constant, so my aerial velocity is conserved. Okay, and okay, so the question is very simple. My angular momentum L is nothing but mr squared theta dot, right? And my m is 3, r squared theta dot is 6, so it is just 18 units. Okay, so question 11. Okay, so the orbit of a particle is given to us. So we are given how r varies with theta. We would have done yes, yes. That is what I have done. So I was just explaining what this conservation of aerial velocity is, and this is L, right? This is just L. So I have done it directly. So it is just 3 times 6, 18. Okay. Okay, so for question 11, so we have this. We are given this r as a function of theta, right? So equation of orbit 1 plus e cosine theta. Okay, and this is a general conic section with L comma E as constants. Sorry, this is L. Okay, and then using this Bennett equation, this orbit arises from a central force f of r proportional to r to the power n. Find n. Okay. So again, what we need to do, we need to change this thing to u. So u is 1 by r, so it becomes 1 plus e cosine theta over L, and then let's find out du by d theta. That will be simply minus e sine theta over L, right? And this implies my d to u by d theta is nothing but minus e cos theta over L. Okay, so the left hand side of my Binet equation, which is this d to u by d theta squared plus u, this then becomes minus e over L cos theta plus 1 plus e cos theta over L. Okay, and so this term cancel out this term, so this simply becomes 1 over L, and this is just a constant. So my right hand side of the Binet equation, which was written over here, so my right hand side is just a constant 1 over L. So mf upon L squared u squared here. So mf 1 by u L squared u squared is simply 1 over L, which implies that I can write my f of 1 over u as minus L squared u squared okay, this was over m into 1 over L, right? This thing. So let us again substitute for r. So this implies my f of r is nothing but minus L squared over ml times 1 over r squared. Okay, and this implies that my f of r is proportional to 1 over r squared. Option A, right? Find n. Why is the substitution of r as 1 by u so useful? Okay, so that helps us in mathematics. Okay, so when we were deriving this equation, let me go back. Right. So when we are deriving this equation, if we do this 1 by u substitution, so what essentially happens is this, you can see this thing. Yes. So this thing cancels out, right? Here and here. These u square terms, they cancel out with each other. Okay, so basically this equation that we get in terms of u is much more simpler, right? This equation, that the final equation that we get, which is independent of t, is much more mathematically concise, right? It only has one second derivative and one u, that's it. So it is just to make math simple, that's it. If you were to write this in terms of r, you can do that, but the equation will become a little lengthier. That's it. You can do in terms of r, no problem. This just makes life easy. That's it. Because this cancels out here. So this cancelling out when taking the derivative really helps. So the first derivative itself is very short, and the second derivative also that we take is very short. We don't get additional components, and we get a very nice, beautiful, concise equation as a result. If we were to deal in R, we can write one equation, but it will be very difficult to solve this. But that's fine.
Excuse me, sir.
Yes.
I understood that the equation that we get is very concise,
Yes.
but the explanation that you gave about that the u square terms get cancelled out,
Hmm.
that is also valid for if we don't substitute r is equal to 1 by u, because here 1 by u square is equal to r square, and u square is equal to 1 by r square. So even if we would have used r square r, then also it would have cancelled out, right?
No. So this derivative that we are taking here, this we would have taken for just r, right? So this would have been r theta
Yes.
dot, right? So derivative of r would have just given you dr by d theta, and for theta dot, that then for theta dot we would have to use this equation, but it would have L upon m r squared here, right? So that will not actually cancel out. You want me to do it? I don't think that will cancel out.
Ah, yes, I understood it. Yeah.
It will not cancel out, right?
Yes, yes.
Right.
So, how was this conclusion reached that r is equal to 1 by u will simplify this equation so much?
Ah, yes. I mean, okay. To be honest, I don't know like how historically how this thing was derived, but I really can't answer that. I mean, I just know that doing this substitution makes it very easy to get the final result, right? So there would have been some very intelligent person who thought, okay, if I substitute r as 1 by u, I'll get a fairly concise equation. So obviously, I think first, okay, you can try this by yourself. Just don't substitute anything for r. Keep r as it is, and let's see what you are getting. And then when you are solving it like that, maybe you'll get some idea. Okay, if I instead of r, if I take some other function of r, like 1 over r, maybe few terms will cancel out with each other. Okay. So of course it wouldn't
Okay.
have been solved like this. Like nobody would have got a dream like let's substitute r as 1 by u. I think firstly whoever was doing this problem, firstly they would have solved for r, and in the final equation that they get, they would have seen, okay, if I just put r as 1 by u, like few of my terms they are getting cancelled out because of this derivative terms that I have, right? And by there maybe somehow they got this equation. But yeah, I to be honest, I don't know this how to explain that why in the beginning I know taking this r as 1 over u simplifies the equation so much. Maybe if I would have derived this equation in terms of r, and then looking at this final equation, it would have been easier to explain or motivate why doing this substitution will make this equation much more concise. So you can try that by yourself.
Okay. Can I get your email ID? If I find an answer to this, I will email it to you.
Sure, sure. I'll type it in the chat box. Okay. So, yeah. So, should we move on? Yes. Okay. So, we have around half an hour remaining. So let's solve few more problems. Okay, so we are given a particle of mass 2 kg which moves under an attractive inverse square law potential, force F of r, and the angular momentum is also given to us. So at r is equals to 5, this its speed is 4 meters per second. Find the total mechanical energy and the type of orbit. Okay, so we are given quite a few things. Let's write them one by one. So first of all, we are given that mass is 2 kg. Then we are given that the central force is minus 50 over r squared Newton, r in meters. Oops, sorry. Then we are also given that the angular momentum L is 10 kg meter squared per second. And then at r is equals to 5, we are given that its speed v is 4 meters per second. Okay, and we have to find the total mechanical energy and the type of orbit. Okay. So what we have to find? Total energy and orbit. What type of orbit is it? Okay. So uh, what is my total energy? So we know for this central potential, I can write my total energy E as half m r dot squared plus V effective r, so which is nothing but half m r dot squared plus L squared over 2 m r squared plus V of r. Okay, and for yes, so this total energy is always conserved, right? It's okay, and also we should note that this term, right? So these two terms combined, half mr dot squared plus this thing, this actually, if you remember, we can write this as, this we did in the last class also, we can write this as half mr dot squared plus r squared theta dot squared, right? And this term is actually our kinetic energy, so this is nothing but half m v squared, right? This was our kinetic energy and this is our potential energy. Okay, so first of all, let's find out our potential energy. We are given f of r as minus k over r squared, and since my f is just the derivative of my potential, so this implies that dv over dr is k over r squared, or my potential v of r is simply minus k over r. You can be accused of f is equals to minus dv over dr, or let me read. Rest of the data is given. We'll be able to find the total mechanical energy. Yes, you are right. You are absolutely right. So that is what we have done. We have this v of r. Okay, and you can note that I have not taken any constant. So I have taken my constant such that v at infinity is 0. Okay, so that is the standard kind of convention. Okay, so at r is equals to 5, my v will become minus, so k is given to be 50, right? This k is 50. So this becomes minus 50 over 5, which is equals to minus 10. And my kinetic energy, let's say T at R is equals to 5, that is simply half mv squared. M is given to be 2 kgs and V is given to be 4 meters per second. Half mv squared will be 4 squared, right? So this will be 16. Okay, so my total energy E is equals to T plus V, which is 16 minus 10, which is 6. Okay, so we have three options here for, okay, no, sorry, two options. So will it be a hyperbolic orbit or a parabolic orbit? Okay, so right, so because our total energy, you see, our total energy is 6, right? So our total energy E is greater than 0. So this is example of unstable system, right? So this leads to hyperbolic orbit. So this is hyperbolic. So option A is correct. Why? Okay. So the question is why? Why energy being greater than 0 means that the orbit will be hyperbolic. Okay, so huh. Okay, so first of all, okay, I'll explain. Let me go below. Yes. So the question is that why does the sign of E determine the orbit shape? So we let me write the effective potential. So V effective R is minus K over R plus L squared over 2 M R squared. Okay, so this is the effective potential, right, for a 1 over R square kind of a thing. Okay, so if my central force has 1 over R square dependence. Okay, then I can write down my effective potential. So this function, you can see it has single, so it will have a minima somewhere. So if I put d effective, sorry, d of v effective over dr is equals to 0. If I do this thing, then if that gives me some minima, that will correspond to a stable equilibrium. Okay, and it can also have some maxima, right? So this, okay, so let me write down. Okay, so this function, v effective of r, this has a single minima at, let's say, some r is equals to r min. Okay, it will have some single minima, and then this function diverges to plus infinity as r tends to 0, right? And this function goes to 0 as my r goes to infinity. Okay. And also for a central force, we know that this r dot squared, this is using the kinetic energy. So this is r dot squared, I can write as 2 over m E minus V effective of R. Okay, I can write this thing, which will be, because this is a square, right? So this is always greater than equal to 0. The particle is confined to regions where where E is greater than equal to V effective, right? So for confined regions. Okay, so what will happen if my E, if my E is equals to this thing, V effective, and my R is a constant which is R minimum, right? Then okay, let me make a table. Okay, so then what will happen? So we have we have chosen the minima. Okay, so this is like we have chosen a minima. So the motion is like we only have single allowed value of R, single allowed R. And so because now the radius is fixed, so the orbit, let me write orbit. So the orbit is a circle. Okay. So the orbit is a circle. So if my energy lies, if my energy is greater than this thing, V effective E, and it is here greater than 0, so what will happen? So my my motion will be such that we are kind of oscillating between R min and R max. Okay, so this will give me ellipse, right? This is like our orbit around the sun. So we have a negative energy, right? But this energy is still greater than our effective potential. Okay, and that, what basically that what that will do, we will have some minima and we'll have a maxima, and we'll just kind of oscillate between these two values of R, like how it happens in an ellipse. And we can also have E is equals to 0, right? And so this means that our particle, this reaches R tends to infinity with exactly 0 speed, with 0 speed, right? Because at infinity our potential, uh, because at infinity you see that our this potential energy goes to 0, and this, and the kinetic energy should then also go to 0 because my total energy is 0. So this is the case of parabola. Okay, E is equals to 1. And finally, if my E is greater than 0, then my particle will reach infinity with finite speed, right? Which is like a hyperbola. which is E greater than 1, and this was E less than 1, right? And this E is nothing but under root 1 plus 2E L squared over M K squared. Okay, and this comes from the conic sections, right? This comes from conic sections, and you can see uh, we had this equation earlier, right? Okay, so basically for a inverse square law potential, depending on the energy, we can have first of all that we can have the orbit to be confined or not confined. Okay, and these two are the example of confined orbits, right? These two are the example of confined orbits. First one is the simplest case, that my radius is fixed. Okay, so my r is just sitting at this r minima, where this effective potential is minimum. So there is only one allowed value of r, and because this r is then constant, so my orbit is circular. Second is that I increase my energy, total energy of the particle slightly, right, which makes it like it is still confined, but now it is oscillating between a minimum r and a maximum r. But because it is still confined, so only possible orbit is an ellipse. And now if we set its energy to 0, we see that it can go to infinity. We can have an infinite position of this particle, and it will reach that positions at 0 speed, so it is no more confined, right? So this gives me a parabola. And finally, if my E is greater than 0, so it can reach r as r to infinity with some finite speed. Okay, and going at finite speed means that the orbit should have been a hyperbola. That's it. Okay, and so here, coming back to our problem, so because E is greater than 0, therefore the orbit is hyperbolic. It is not, what do you call it? Yeah, it is not a bound orbit. It is like an open orbit. So it's like a hyperbola. So energy has to be negative, right? If it is negative, then it would have been a bound orbit. So right now it is like an open orbit. Okay. Is that clear? Okay. Okay. So let's move on. So we have a particle which moves with r is equals to b constant and theta t as ct squared, where c is a constant. So find its acceleration at time t in terms of r cap and theta cap. Okay, so a very simple problem. We have already seen how our acceleration has two components. Let's write them again. So the r component is simply r double dot and r theta dot squared. And then we have theta component. Okay, so r is equals to b, which is a constant. So this implies r dot is equals to r double dot is 0. Okay, and theta is ct squared, which implies theta dot is 2ct and theta double dot is 2c. Okay, so my radial component ar is just minus b and theta dot squared is 4c squared t squared, and my theta component is just r theta double dot So this is B2 BC, and then R dot is 0. So that's it. Okay. So combining this, I can write my acceleration as minus 4 BC squared T squared R cap plus 2 BC theta cap. So this one. Okay. So just a direct substitution of R and theta, like very straightforward problem. Okay, now let's solve last problem for today. And then here we are given a logarithmic spiral R as a e to the minus k theta. We are given that a and k are greater than 0, while theta t is omega t, and omega is a constant. Find its speed at time t. Okay. So my r dot, which is nothing but dr by dt, will be a, and then e to the power minus k theta. Okay, so I'll have, if I take its derivative, so it becomes minus k will come here, right? And e to the power minus k theta, and then d theta over dt, right? So d theta over dt, and d theta over dt. So from this equation, I can write d theta over dt is omega. So my r dot I can write as a times minus k omega e to the power minus k, and theta I can write as omega t. Okay. Or let me write theta. And then this a e to the minus k theta, I know is simply r. Oops. So I can write it as minus k omega times r. Okay. And so my radial component of velocity is just minus k omega r, and my theta component v theta is just omega times r. That's it. So I have these two components, therefore my speed becomes under root vr squared plus v theta squared. And if I do this thing, so I'll have k squared omega squared r squared plus omega squared r squared, and take its under root. So my speed becomes r omega under root 1 plus k squared. This one. Okay, so that's that's the speed of my particle, which is moving in a logarithmic spiral. So okay. Okay, so do you know why these logarithmic spirals are relevant? Because just like Fibonacci sequence and other mathematical things, like these logarithmic spirals also show up in nature. So because we have we have some shells, right? You have seen some seashells, they have this spiral kind of a shape. And like the galaxies that we have, or the hurricanes that we have, they are also they also have this kind of logarithmic spiral kind of a shape. Okay, so you can see as your theta is increasing, so your radius is decaying exponentially. Okay, so you can, what you can do is you can plot this function logarithmic spiral. You can plot this function on MATLAB or whatever language you want to use, and then you can look at its shape, and then what you'll realize is that it looks like galaxies or volcanoes or shells or like something, like things that we see in nature. Okay, so yeah, so this can form a problem for some galaxy, for example. Okay, so this was it. This was the last question, and if you have any doubts, you can ask, or we'll meet next Saturday, same time.
Uh, why is a spiral such a special shape?
Um, I
Like we
mean,
observe it at so many places, and it sort of originates from one point, or yeah, originates from one point.
right, right. So, I mean, that is how nature is, right? Like we have, as I said, we have Fibonacci sequences, we have these golden ratios that we see in flowers. It's kind of interesting, right? Like why these shapes, like from all the way from galaxies to the shells that we have, we see these things, we see these patterns kind of repeat on different length scales, right? I mean, I don't know why they follow this logarithmic spiral, but it's actually very cool that in very different kind of uh, systems, we see that this spiral follows this same equation, which is the logarithmic spiral. Yeah, but I really don't know why only this logarithmic spiral, why galaxies don't have some other kind of equation. I don't know. It, of course, it has to be related to some kind of stability, right? This shape must be very stable. Uh,
Yeah.
but why is it stable compared to others? I can't really comment on that. So, but yeah,
Why the
yes. Sorry.
Yeah, continue.
No, no, sorry. Please.
Why in nature is that so many things look for stability. For example, even in chemistry and biology, we come across things. For example, compounds which were formed because they were in the most stable configuration,
Yes,
and
yes.
even evolution follows from this stability.
Yes, yes. So it is like a law of nature, right? And for a law, we really don't have any explanation, right? Like for example, we have this law of thermodynamics that the entropy of a system has to be maximum, right? That this entropy always increases. We cannot really explain why. We just know that it does, and it is a law of nature. So this stability, yeah, stability you can assign to like the minimum energy, but why nature tries to minimize energy, like we don't know, right? It is just a law of nature that energy has to be minimum. That is like its stable configuration. But why we don't really know, right? So you
Maybe because
yes.
yeah, you continue.
No,
Continue.
no, sorry. Please.
Uh,
I'm speaking for 2 hours. Let's give others chance.
yeah, maybe because nature is optimizing for maximum entropy. That's why stability is a consequence of it.
Yes, but then I can again ask why maximum entropy? Why will nature want to have a maximum entropy, right?
That's something that we have observed. We
Yes,
cannot
yes.
say why. That's an epistemological limit.
Exactly. So when we observe several phenomena, and then what we do is we say this is how nature behaves. This is a law of nature, right? So we call it a law, and it is a law, and then you cannot really explain why this is a law and not something else, right?
Okay.
Yes. But yeah, I just wanted to share this thing because I really find it fascinating that these logarithmic spirals exist everywhere, and many of us are not
Yeah, it is
actually aware
fascinating.
of this thing. So I think it's interesting. So you can have a look,
Yeah,
and I hope you'll also find it interesting.
yeah. Even they are observed on these shells of marine
Yes,
creatures.
yes, yes, yes. Okay, so I'll see you next week then. Have a
Yeah,
nice
I
weekend.
have a
Yeah, yeah, sure.
yeah, I have a request about regarding the timings of the class. Is it possible to shift it 15 to 20 minutes later? Any chance?
No, actually, these timings like they get fixed prior to the starting of this course, and I can change it for one or two sessions upon special request, but like a permanent change of timings, I don't think it will be possible. But you can always join late. That's not a problem with me, right?
Yeah,
If you are running late, not an issue. Join late, and these videos I think are uploaded to YouTube. So the part you miss is you can again go back to YouTube and watch it. So the starting 20-30 minutes.
yeah. Okay.
Yeah, but I'm really sorry. I mean I'm okay with it,
No,
but
no problem.
this is how the this NPTEL works. So
Uh, no problem. I'm also fine with 4, but it was more convenient for me to join at 4:30. I I have college till 3:30 now,
oh
so traveling time must also be
yeah,
okay.
I'm really sorry.
No problem.
Anyway, so okay. Any other thing?
Nothing. Nothing.
Nothing. Okay. Okay. Nice talking to you. I'll see you next week. Enjoy your weekend. Bye bye.
Thank you. Bye.